Cryptography Fundamentals Part 1 Groups, Rings and Discrete Logs. The problem with cryptography is that many miss some fundamental knowledge that will allow them to fully understand the key operations that are used. So, in this series of podcasts, I will try and explain some of the core concepts that have secured our online world. Every single time that you connect to the internet, the privacy and the trustworthiness of your connection are dependent upon these simple, magical cryptographic operations. So let's start with numbers, because it's all about numbers. And in our world of numbers, we have n, natural numbers. These are positive and negative integer values. -5, -93, +49, and so on. Then we have z, which are the integers. I'll explain the difference between natural numbers and integers in a little minute. R are the real numbers, 3.942, -2.694, and so on. And C, the complex numbers. Natural numbers, of course, can go from -infinity to +infinity. That's a lot of numbers. So often we try to constrain them. So the integers, or z, contains numbers, these numbers within a ring. And the ring might go from 0 to 16, and then 17 goes back to 0, and so on. And if we go to -1, that is 16, and -2 is 15, and so on. So in cryptography, we use Z to represent our ring of numbers. Often it's represented by a double struck or a blackboard bold symbol. It has the two lines in the center which will embolden the Z. And for this, we typically define it as a group of numbers. We represent our groups by Z subscript n, and those are the numbers that go from 0 to n-1. So Z subscript 7 is 1, 2, 3, 4, 5, 6. Sometimes we can ignore the 0 because it can cause problems within cryptography. So we'll just leave that one out. So Z_7 is 1, 2, 3, 4, 5, 6. There's also another group that we can use called the multiplicative group of integers modulo n. I'll explain more about that in a future podcast, but it's represented by Z subscript n superscript star. This is the group of numbers that do not share a factor with n. So Z_7 is 1, 2, 3, 4, 5, 6, and Z_16 star will be 1, 5, 7, and 11, because 2, 3, 6, and so on are multiplicative factors with inside 16. So a group is basically a set of integers, and where we map one group to another. If we think about these as two sets of A and B, then we create a mapping from the numbers in A to B, and vice versa. For encryption, we want to create a one-to-one mapping from every value in A to B, and then for us to be able to reverse this back from B to A. So if we have a set of numbers A is equal to 1, 2, 3, 4, we might map these to B equals 2, 4, 3, 1. If we have a value of 1 in A, it will create a mapping to 2 in B. Then in B, we would map back from 2 to 1. In cryptography, we typically want to make it easy to go from A to B, called encrypting, but difficult to go back from B to A, decrypting unless we know a secret. In this example, I have used a discrete logarithm mapping with a base generator of g and a prime number of p. For this, I have little b is equal to g to the power of a mod p. It's a fundamental operation, and it was the core of the Diffie-Hellman key exchange method. For this mapping, we have 1, 2, 3, 4, mapping to 2, 4, 3, 1. And I've used a g of 2 and a prime number of 5. So let's try them. For a value of 1, b is equal to 2 to the power of 1 mod p. That's equal to 2 mod 5, which is 2. Now try 2. 2 to the power of 2 mod 5 is equal to 4 mod 5, which is equal to 4. The mod is a remainder of a division, and with a division by the value, and then we take the remainder. So let's try 3. 2 to the power of 3 mod 5. 2 to the power of 3 is 8, mod 5 is 3. Then 2 to the power of 4 mod 5 gives us 16 mod 5, and as you should know, that's 1 as a remainder. So the values that we have, 1, 2, 3 and 4 map to 2, 4, 3 and 1. That's great because we have a one-to-one mapping from A to B so that all of the values map and there is no dual connections. This will also be cyclic, and where 1, 2, 3, 4, 5, 6, 7, 8 will map to 2, 4, 3, 1, 2, 4, 3, 1. So we constrain the values within a finite field of between 0 and 4, and this is p minus 1. And we can see that this gives a one-to-one mapping for each of the elements in one set to another. Every value in b can then be reversed back to its original value, hopefully. To reverse, though, we would need to compute the inverse log of the value in b for mod p, and this is not so easy. Log to the base g of b mod p. And so this is the core difficulty in the discrete logarithm problem, and it is the problem that secures the internet. To show the difficulty in this, we can use a prime number of 2 to the power of 255 minus 19 and a g value of 2. And in the related blog post, I've posted a value of b for a certain x value. 2, 5, 4, 4 goes on for a lot of numbers, and we have 2, 8, 8 at the end. For this, it's actually extremely difficult to find the value of x that we have used to create this discrete log value. So you can see now why it's so important to create a function that allows us to be able to map from one set to another and then back again. So we've covered the basic concepts of a group, a Z, a ring, and also we used a mapping of discrete logarithms to map from one group to another. I'll continue on and we can investigate more of the amazing world of cryptography. Thank you.